Welcome to this November meeting of the modeling sub-team of IARPIC. IARPIC, for those of you who are not familiar with it, is an interagency Arctic Research Policy Committee, which is a federally mandated group of leaders representing 16 agencies across the U.S. government that have a stake in the Arctic. IARPIC Collaborations is the associated outward-facing platform that facilitates and encourages collaborations between scientists from federal, state, academic, NGO, industry, indigenous, and international organizations to address problems related to the Arctic. And within IARPIC Collaborations, the modeling team aims to enhance understanding of the integrated Arctic system through the use of regional and global Earth system models. So today we'll be discussing the application of machine learning techniques to the modeling of the Arctic Earth system. Machine learning is changing many aspects of science practice in quite unprecedented ways, and numerical modeling is no exception. So it would be good to get some examples of how machine learning is being applied to Earth system modeling. So we'll have two speakers today, and followed hopefully by some time for discussion. We'll start off with Maria Molina. Dr. Molina, she is a research scientist at NCAR and a member of the Catalyst team. She received a PhD in 2019 from Central Michigan University in Earth and Ecosystem Sciences. She was also a research broadcast meteorologist from 2009 through to 2017. And as I said, she's now a research scientist participating as a member of the Catalyst team at NCAR. So with that, I'll hand it over to you, Maria.
Thank you so much, Wilbur, and thank you all for the invitation. It's an honor to be here with you today and to get to talk about some machine learning applications for the Arctic. So I'm sharing my slides now. And I will say I am not an Arctic expert at all. My background is in atmospheric science, and I have very much focused on the mid-latitudes and specifically across North America, looking at severe convective storm environments. But over the last couple of years, I became very interested in machine learning and pursued a postdoc where I could really specialize on the application of machine learning for Earth system science questions. And that has really opened up a world of new research questions that I can explore and new collaborations that have been very exciting into topics that I, again, am not familiar with or an expert in. And so as an example, today I'll be sharing some work that I'm contributing to that's being led by Alice Duvivier and Marika Holland within NCAR. And this is going to be an Antarctic focused project, but otherwise I work with a very large group across NCAR and specifically within the Climate and Global Dynamics Laboratory and our DOE funded cooperative agreement named Catalyst. And we really focus on modes of climate variability and seeing how they are changing and also exploring their predictability using machine learning. So I'll also be sharing some of the work that's currently ongoing with some of those efforts. But here again, so my talk today will be really on machine learning methods as applied to Earth system modeling and including that Antarctic focus just for you all. And so machine learning itself is not new. We know that it's been around for quite some time. In fact, the term machine learning was defined back in the 1950s, but there are several recent innovations that really enabled significant advances within machine learning, and especially since the 1990s. One of those advances included GPUs, which really have helped expand the sizes of machine learning models by accelerating computation. High quality and large data sets that are labeled and really created for the purpose of benchmarking machine learning models has also been a big advance. One of those large data sets is ImageNet, which was created or led by a group out of Stanford University. And that really led to the creation of these large data sets that allow us to benchmark models and see how to improve performance for various very specific tasks and competitions. And there's also been advances within deep learning itself, including loss functions and other hyperparameters that have enabled better training or more stable training and have actually helped us within the Earth system sciences to apply some of these tools and make advances. But there's several important considerations to keep in mind when we're using machine learning and deep learning methods in the earth sciences. Right, so in industry, there's really the objective of optimizing a certain task, and sometimes those may be for a private company, and they have a very specific task or client that they're trying to optimize for. But for the earth sciences, we really need to incorporate these three considerations or principles. So for example, incorporating our knowledge of the Earth system is important, and also some physics consideration and constraints. We also need to ensure that the models that we train are robust. And so this includes robust to extremes or outlier events that may have not occurred in the training data. So what happens when a machine learning model that was trained under a certain climate encounters extremes and perhaps some as we move into a future warmer climate? And also we need to understand why a model is able to perform well, right? So we need to be able to explain the decisions made by a machine learning model. And at times that may require us to use machine learning models that are inherently interpretable, that we can describe a bit easier. But in the case where we have a very complex model that's needed, such as a very deep neural network, then we may need to turn to explainable AI methods. So there are tools to understand why our models are performing in a certain way. And so machine learning can really fit in different areas of the Earth system modeling pipeline. So if we were to divide the Earth system modeling pipeline into 3 steps, where we have an input, the step where the model is running, and then eventually the output, we can apply machine learning to each of these steps. So here I have some very brief examples. So for example, before we run an Earth system model, we can actually use machine learning to improve our observations. And this could also improve the initialization conditions for this numerical model that we'll be running. And so there has been quite a bit of work done in this space. And here I share an example of a paper that was led by a graduate student in collaboration with scientists at NCAR, performing deep learning based observation quality control. And they really focus on improving observations of precipitation over mountainous terrain due to the limitations out there. And we can also apply machine learning to the model when it's running. So we can, for example, train a machine learning model to perform some sort of physical parameterization that can either reduce the cost of running that numerical model, and increase its speed, or improve its accuracy in representing that process. So for example, here I'm sharing another paper from a group at NCAR that was recently published for machine learning, the warm rain process and representation of clouds. So this was published recently in James. And then we can also apply machine learning once our numerical model or dynamical system has finished running and we have the output from that model. So for example, if we were to run E3SM and then take its output, we can then do things with that numerical model output. And so here I'm sharing an example that I recently published, applying deep learning methods to classify severe convective storms using very high resolution model output. This was work done during my postdoc. And here I did some benchmarking to assess how well a deep learning model could generalize in a changing climate. So here's the 3 examples or applications that I'll be briefly sharing with you today. I'm going to be quickly going through them because of our limited time, but I do welcome questions at the end of this talk. And some of these projects are very much ongoing. So I also welcome your suggestions or comments for improvement. So the first project that I'm sharing with you here, and I actually will go back. So the first project here involves the characterization of a large scale environment. The next 2 will be supervised learning approaches where we'll be performing classification or prediction. But in this case, this project involves unsupervised learning. So if you can think of an approach like clustering or k-means clustering, for example, being one approach. The approach we use here though are self-organizing maps. And so essentially what we do with a self-organizing map, this is an artificial neural network that we initialize. And for a self-organizing map, you would arrange neurons or nodes on a two-dimensional lattice like this. So here, this diagram or schematic has a 3x3 architecture. And so we essentially have 9 nodes. And what we do is we feed in our data, and every time it sees an example in this application, we would measure some similarity score. And so these nodes would eventually be nudged in a way that they are grouping together patterns that are similar within that input vector. And there are, of course, numerous hyperparameters that can be tuned and tweaked, and I'm happy to answer questions about that as well. But here's an example application of this type of method. So the project that we are exploring this method with involves the identification of polynyas in the Antarctic region and certain sea ice patterns that lead to the development of polynyas, right? So my understanding as a non-Antarctic expert is that helps with deep water formation, which is of course a very important process in the Earth system. And there are certain large-scale patterns that potentially precede the development of these polynyas. And so that's really what we were trying to understand a bit better. And so what has been done for this project, this is being led by Alice Duvivier. My contribution is really just the self-organizing map expertise, is they're looking at several different regions that are Antarctic marine protected areas, and they're classifying some of these different synoptic scale patterns across Antarctica. And so they are using a large ensemble for this. This slide here is just some preliminary work. But again, what they're doing is they're looking at those large scale patterns, and the training actually takes place using sea ice data. And so what's great about a self-organizing map is that you can train using one type of variable, for example, sea ice data, and then go back and look at other variables in your data set to characterize what was associated with that very specific clustering of some sort of variable. And with self-organizing maps, another advantage and a difference to something like k-means clustering is that these nodes show you transitional modes in between different patterns. So for example, we would infer from this analysis that a certain node, such as this one on the top left, would be somehow related to the neighboring nodes and less related to something farther away. And so that, of course, requires some additional analysis. But now we turn to supervised learning. And so for supervised learning, all that means is that essentially you have some input data or some variables that are going to be used to train a machine learning model, and you know the answer ahead of time. And so we train a machine learning model to learn that relationship between your input and your output. So that could be with some sort of lead time or simply some sort of classification, such as what we're doing here in this case with no lead time. And so really the objective of this study was to take high resolution model output, taking a look at severe convective storms, and then classifying them into 2 different classes. These are strongly rotating storms or non-strongly rotating storms. And the reason we care about storm rotation across the US is because the stronger a storm is rotating, especially within its updraft, the higher the possibility that that storm could produce a severe hazard, such as large hail or tornadoes. And so we wanted to see if a convolutional neural network, which considers some of the spatial properties of our data, could learn to classify storms in this way. And we trained it under a current climate scenario and then evaluated it with future climate storms to see how robust this type of approach would be to extremes and storms that were created or developed in a future model simulation under much higher moisture content and much warmer temperatures. And so we found that this convolutional neural network could perform very well at this classification task. And in fact, it could also stay skillful in a future climate, but there are numerous caveats associated with that, of course, including that we use a large number of input variables and that we're looking at very small scale features here. But we were also able to apply explainable AI methods after that. So we were able to output these sorts of maps where we're looking at gradients within our convolutional neural network. And we found that the network actually learned some physical properties of convection. And so that was really promising. So in this case, you're looking at U and V winds, so winds in the X and Y direction on the horizontal at 3 kilometers. And the network identified that there's a couplet of strong rotation near the center of storms. And so it was really relying on that identified feature that it learned to perform this classification task. So that was very promising. And then my last example that I'll be sharing with you is a project that I'm currently in progress. And here my objective was to perform prediction of subseasonal prediction errors of temperature and precipitation. And I do have results for precipitation as well, but I'm just going to share temperature with you right now. And what we're doing is we're essentially training another type of convolutional neural network. But in this case, this architecture is called a U-net. And the reason it's called the U-net is, of course, because it's shaped like a U. And the objective or the purpose of having this type of architecture is that there are certain cross connections. So for example, our input and first shallow layers of the convolutional network would be directly connected to some of these convolutions towards the output. And so this helps address vanishing gradients, which can be an issue when we have very deep neural networks. As that signal is propagated during the training process. And we found that this approach really helped address that issue. And so what we decided to do was go ahead and use our inputs of precipitation anomalies in this example for this slide that I'm sharing here. And then we wanted it to bias correct those anomalies. Essentially, we wanted to improve upon those forecasts. And so what we ended up doing was predicting the anomaly error within our fields. And so we're using global fields here. So this is a global precipitation product available from NOAA that combines satellite information and rain gauges, and then our CESM2 hindcast data. And we saw that our neural network could actually learn to predict these precipitation anomaly errors with skill. And so here we're looking at weeks 1 through 3 as input, and then predicting our week 3 precipitation anomaly errors. If we take a look at performance for temperature, it was very excellent. So here we're looking at our Pearson correlation between the errors for the temperature at week 3, and we found that the neural network was able to perform quite well and consistently across seasons, which is also surprising because certain seasons tend to have higher predictability over certain hemispheres. And the same was true for our precipitation model. So again, very promising approaches, and still further work and investigation needed to better understand why or what this neural network is learning during this training process. And so I did some thinking about potential opportunities for the Arctic, and this is my last slide. But we know that we can use machine learning to characterize large-scale patterns over the Arctic, potentially analyzing how those patterns are changing. We can also classify sea ice patterns as well and look at different types of sea ice and perform error prediction for Arctic variables. I'm not quite well versed in how much error there is in the Arctic. I would imagine so, given that it's a less densely populated area, but for example, for precipitation on the subseasonal timescale, skill is very low from our numerical models, but we are seeing that we can potentially improve predictions there. So hopefully that can help other regions of the globe as well. And with that, I will stop. Thank you.
Terrific, Maria. Thank you very much. This was an excellent overview of the possibilities for machine learning applied to Earth system modeling. You've always been well on time, so I was opening it up for a couple of questions, but otherwise people can put them in the chat, and maybe you will be able to answer them in the chat also. So anybody has a pressing question for Maria?
Yes, I have a question. Can you hear me? It's about beginning of presentation regarding sea ice production. So it is my understanding that you have information about sea ice production.
I'm sorry.
From where? You classified it.
I'm sorry.
Where did you get information about sea ice production? How it
Oh,
was
okay.
calculated?
Yeah, so this is output from our CESM model. So I am not inferring that it is skillful representation of sea
So
ice.
it's model
Yes.
results.
Model results,
Okay.
correct.
Okay. Now you
Mhm.
classified the synoptics process for 10 groups. What kind of useful information that classification provides? If you already have a model, and you could not improve the model in this case.
Yeah, so again, I will caveat this with that I am not the Antarctic expert, but the objective here is to just classify these large scale patterns in a way that, you know, instead of me as a human going in and looking at some of these regions and, you know, it's a lot of data. There's I don't know how many ensemble members, but it's terabytes and terabytes of data. And so this really helps with an automated way of learning what these patterns are, and then seeing potentially how they are changing. And from a model perspective, we can see if certain ensemble members are more consistently outputting variables or patterns are in a certain node or a certain neuron within that artificial neural network. So there is some analysis that can take place on model results. As far as analysis of how skillful the model CICE is, I think at that point you would need some sort of observational product. I don't know. But again, it's really just to learn what these patterns are, try to get some evenly distributed artificial neural network. And by training using sea ice patterns, then you can see whether certain large scale patterns consistently produce that specific sea ice pattern. And if that specific sea ice pattern is related with polynya development, then perhaps that can help with predictability or so. But again, I'm not an Antarctic expert, so I can't speak to that aspect of the project.
Yes, and
Does
just to
that
clarify,
help?
Jake will definitely talk a little bit more about CIs in his presentation. Yvette, do you want to ask your question?
Yes, if I understand correctly, you use machine learning to define some technique that envelop a lot of different approaches, like neural networking that is pretty old now in, you know, it's more than 10 or 15 years than Seascape has seen those technique used. So I would like to ask you, what is so different in machine learning? Is that just an envelope of different techniques for different purposes, or what is so different from what was used 10, 15 years ago with the same meaning of looking a region and classifying some region with similar properties?
Yeah, so self-organizing maps, you're right, is not new. It's been used for quite some time. And in fact, I would say probably longer than 10 years ago. Hello? Oh, yeah. And so I would not say that that is particularly new. What is perhaps newer are some of the later methods that I showed. So for example, the UNet architecture that I use, I'm using a very similar architecture to the one that was used in the nominal paper that introduced them in about, I think, 2015. And what's so new is just the technology that has allowed us to build these deeper and deeper networks that can learn these nonlinear mappings and relationships between our input variables and learn some of these spatial patterns in our data using, for example, convolutional neural networks. So for self-organizing maps, It's just another tool in the toolbox. It's an unsupervised method that can be coupled eventually with a supervised neural network down the road. So for example, you could imagine a situation where you would use a self-organizing map to generate these classifications that can then, which are these different nodes, which can then be used to train a neural network that precedes that and can predict those different classes of large-scale patterns. But you're right, self-organizing maps are not new. They've been around for quite some time, but they're still a very useful approach to, in your machine learning toolbox, in my opinion.
All right, great. Thanks, Molly. Thanks, Maria. Great, nice discussion. And we'll continue that after Jake's presentation. So I'll hand it over to Jake. So Jake Nichol is a graduate student at the University of New Mexico. He studies computer science, and he also has a Bachelor of Science degree in computer science from UNM. And he's currently a graduate intern at Sandia National Laboratory. So he basically juggles research responsibilities with his studies. And he studies computational causal inference for Earth system science, and that's what he will be talking about in his presentation applied to the Arctic. Go ahead, Jake.
All right. Okay. Yeah, so thank you for the introduction. Yeah, I'm going to be talking about two separate projects in this work, which are, I think, nice applications of exactly what we were just learning about, some explainable methods. And the focus of this work is not necessarily to predict well. We want our methods to predict well, but we're really interested in what they can tell us about the data. That's what I'm interested in studying. So machine learning and causal discovery for comparing simulation and Arctic, simulation and observed Arctic data. I'm going to talk about first the problem that we want to address, the goals for our methods, and then I'll discuss these two methods. One, the random forest feature importance. This is work that we conducted a little more than a year ago. And then some current work that's, and I'll show some preliminary results of method 2, causal discovery graph comparison. And I'll show the results so far and discuss future work. So the problem that we're wanting to address is the Arctic sea ice extent is declining over every decade. And this has impacts around the globe, the amount of sea ice. As many of us here are probably aware, the minimum sea ice extent in the Arctic is in September every year, and then it starts growing again in the winter. And so predicting how much sea ice extent there will be in September and when roughly that minimum will occur is very important for climate dynamics around the globe. In 2017, this study was published showing that 11% of model runs from CMIP5 were predicting sea ice extent decline as quickly as we are observing. So most of them predicted that the sea ice extent was declining slower. In this work that I'm going to be presenting, we are examining the Energy Exascale Earth System model, which is the Department of Energy's flagship coupled climate model. The goals here are, first, we want to quantify the impacts of features that relate to Arctic sea ice extent. Features, for those who aren't familiar with machine learning vernacular, are just variables. And then we want to train models. Well, the quantifying those impacts is training the models. And then next, we want to compare the results of each model between simulation and observed data sets and see where the differences lie. The nice thing about machine learning is that it can learn these nonlinear dynamics in data. It can take a holistic picture of a full data set and evaluate all the interdependencies. And so then our final goal, eventually, we'd like to improve physics-based models of the Arctic climate by learning from our results in this work tuning the models differently, and see if they improve and see how it shifts the machine learning model's output after the tuning as well. So the data that we collected are these features here. We collected the same data from observed data sources and from 5 E3SM simulations. These are the historical ensemble runs from E3SM, which are over the last 165 years. So that's a total of 6 data sets that we're going to be comparing in this work. Here's a look at what the time series of sea ice extent in the Arctic looks like between observed and E3SM simulation runs. And all of the data that we are inputting to our methods here are time series like this. And so to get time series from the spatiotemporal data, we right now are just very naively taking an average over the whole Arctic, average value for each month, and that creates this time series. So the first method are random forests. Random forests are what we call an ensemble method. They are a collection of another machine learning model called decision trees. You can think of decision trees as like sort of like a game of 20 questions. It's looking at the data and testing the difference between what the answers are, how predictable something the end output is by looking at certain variables, and then branching down through this tree and looking at more variables. And then in a random forest, we take many different decision trees, many different games of 20 questions, and we see, in that example, in that analogy, what are the right questions to ask? What's the right order to ask them? Those kind of things, and we can get the most efficient, most predictable set of questions to get to the answer we want. And what's really great about random forests is they provide what's called a Gini importance or a feature importance, which tells us how predictable or how predictive each feature is. So, and we can get a ranking. What's the most predictive feature for predicting sea ice extent in our case? And so we take each year's summer data. We looked at June, July, and August. And we wanted to use those data to predict September sea ice extent. We pass that into the random forest, and we get a regression on the top here, which tells us how well the model fit the data. And it is a prediction. And on the bottom, we get a set of feature importances or Gini importances for each feature. Now, I'll overview our second method. This is called causal discovery. This is a very new and growing field right now that's just barely being applied to Arctic or to climate data. The idea here is that we have a real world process that we can collect observational data from. We train a causal discovery learning algorithm on that data, and it produces a graph where all of these nodes in the graph, x1, x2, and so on, are different variables that we're examining. And these arrows represent the estimated causal relationship between those variables. So our methods are going to look like this. We first pass observational data into random forests and get a set of feature importance. We then do the same for our simulated data sets. And then we can compare the feature importance sets between these sets. And very similarly in the causal discovery, causal network example, we have observed data on the left, and in this picture we have 4 different simulation runs. They all produce a set of 5 different graphs, and we can make comparisons between those graphs. How different are they and why? This is an example of the results from our random forest work. So these are all feature importances, and I'll walk through the different parts of this graph because there's a lot to look at. So each column separated by the dashed lines are different data sets we have observed in the 5 different simulation runs. In the top, these boxes for each column show how well the random forest fit the data. That's important because it validates the feature importance. If it fit well, then if it didn't fit well, we wouldn't have any confidence in our feature importances. And then these bars with all the different colors are the different features. So you can see their color coding in the top. And you can see there's quite a bit of variability between these data sets. And we would expect some variability in the simulations, but we would hope for some general patterns to persist. And there are some important patterns that are consistent between these data sets. So to describe that, first I'll point out this blue line at the bottom that's horizontal. That represents a random variable that we included in the data, and a random variable should have no impact on the predictability of the model. So that is our theoretical sort of zero importance. Anything above that threshold is considered important. And in this case, what's good to see is the same 6 variables are all important across every data set. So that's nice. The magnitude of their importance is very different. In the observed data, it found that sea ice extent, sea ice volume, and sea surface temperature were the most predictive of sea ice extent in September. And in the simulation data sets, it sort of ranked everything very similarly, and then put a huge amount of importance on sea ice volume for being predictive of sea ice extent, which it makes sense intuitively. We just don't see that replicated in observed data. And then here are the results from our causal discovery work. These are sort of in progress results. And you can see that our algorithm produced these 6 different graphs, one for each data set and all of the different variables. And in the top, we have this F1 score chart. This is our first pass at trying to evaluate the differences between these graphs. An F1 score is a pairwise graph comparison metric. So a higher score towards 1 shows that 2 graphs are more similar, and then 0 means that they are totally dissimilar. And so we see that the simulations are all fairly similar to each other and have fairly similar similarities between each other. And then the observed data is a little bit different, but not a lot different. So this is encouraging that we're capturing some differences here and similarities. The next steps are to develop some node-to-node similarity metrics and understand what are the differences between 2 graphs. When we look at one node in 2 different graphs, how are their connections to other nodes different? And that'll tell us more meaningfully why these data sets are different from each other. And so yeah, that's all. So I'm open to questions now, and I'll include here a reference to our random forest work that we completed a little while ago.
Excellent, thanks, Jake.
Yeah,
that was a really nice overview of this kind of work applied to the Arctic. Really appreciate that. Let's open it up for a couple of questions for Jake specifically, and then we can move into the discussion. So I guess I have a question. So your importance kind of chart indicated that the winds are not important for sea ice predictability, right?
Yeah, that's right. Yeah, they're in every single data set here. And in fact, so this is just, we have 3 of these charts in our paper, one for July, June, and August. And in all of them, in every data set, the winds were found to be unimportant. So I'm a computer scientist. I don't know why that's surprising, but that was consistent. So. Right.
So are those winds averaged over the entire Arctic? Or, I mean, you can imagine that especially the winds in certain gateways will have an impact on the amount of sea ice.
Yeah, and that may be exactly why. So that's a big, that's an important future step for this work. This was Pan-Arctic data. And so, yeah, little differences like that might have averaged out and we lose those key differences. So yeah, a next step is going to be separating all of these out into all of the different important regions within the Arctic. which will work well for this method because random forests are very good at handling lots of features, as long as you have enough other data as well. So, yeah.
Right, great. Thank you. Are there any other questions for Jake in particular? I don't see that Vladimir has a question in the chat. Do you think we have enough CS observations for machine learning?
Yeah, that's a good question. It depends on, so obviously the data resolution varies between observation and simulation. And in observational data, the resolution varies by quantity. Some of them are as often as, are measured by satellite as often as 4 times a day, and some 4 times a year. So that poses a challenge. In this case, we were looking at monthly data. And so the answer broadly is, this is because of our fit metrics are nice in the top. These models fit the data well. So random forests work well with this amount of data, with this much data. But other methods like neural networks, deep learning methods, are going to struggle with this amount of data, from my understanding. There are some papers that have been published predicting sea ice extent with deep learning models. And I believe they supplemented a lot of their data with simulation data in those cases.
Great, thank you. So let's maybe open it up for a general discussion. There are still a couple of questions in the chat, so maybe we should start with that. Hazel, do you want to ask your question?
Sure, that would be great. And so I think it's for either Maria or Jake. I think you'd have sort of a different perspective on this, but just wondering about this strategy. How do you think about, when machine learning is applicable? Because I think it's a hot topic right now, so it's easy to say, whatever the issue is, oh, we should apply machine learning here, and sometimes it's a good fit, and sometimes it's not quite the right tool. So I'm wondering how you approach that, and then once you've targeted something, how do you find where you would have the most impact?
Jake, did you want to go first or want me to go first?
You can go ahead. Yeah.
Okay, great. Yeah, I think for me personally, it depends on the question, right? And so I kind of start with, I maybe have a decision tree or a random forest that my brain goes through, right? So, and I ask a series of questions, right? So first, is this an unsupervised method or supervised method? Like what approach do I want to go? And then that kind of starts to group what types of approaches are available in machine learning. And I also ask myself whether machine learning would be needed. So the question of data was brought up, right? So the sample size is important to consider for certain deep learning methods, particularly. Limited sample size is not good for deep learning models, but there are also then other approaches that can be supplemented at that time, such as transfer learning, where you could train with one data product for some time and then take those pre-tuned weights and then keep training with a different data product. And so that can also help a bit with generalizability, if that is even a word, but to help your model generalize between data products and not overfit to a very specific type of product. And so that's kind of where my brain goes. I just start thinking about the questions and how nonlinear the system is. If I have a lot of different variables and I don't really know which one is most important for the problem at hand, I would go through a series of hyperparameter tuning where I evaluate whether my model skill improves or decreases based on certain input variables. And that can also help me understand the characteristics of my data, what's really important, and just learn about the system in that way. And so, for example, I'll also quickly mention that the deep learning model that I shared, that I had classification of thunderstorms and then evaluated in a future climate, I actually found for that model, if I wanted it to perform well in both climates and be robust to extreme events, I needed more input variables or features like Jake described in machine learning language terms. So the more variables I had 20 input variables to train. That really helped the network be robust to extremes. And performing explainable AI methods, I learned that overall certain variables were generally most important, but when faced with extreme events, suddenly other variables became more important. So the network learned to ignore variables during certain cases because it learned those variables were not as reliable for those extreme cases, and it would turn to other variables. So that was really interesting. So perhaps sometimes you don't have to choose input variables, but of course, always good to keep your domain knowledge at hand. And Jake, sorry I rambled on and on. I'll let you add.
No, I thought that was great. So as a computer scientist, I'm always very hesitant to make assumptions about what machine learning can learn that we can't learn from the physics in a system. And so my bias is towards learning about the data rather than coming in and trying to replace our physics-based models with machine learning techniques. We are starting to explore some of that to try to replace some of the slower parts of models with faster machine learning methods where that works. But that hesitancy comes because machine learning models can be very predictive sometimes for completely the wrong reasons. And that's part of why having explainable methods or explainability tools to describe why the method is learning what it's learned can be really helpful, because they can just show, when you apply those, you can learn that, oh, it's focusing on some metric that just isn't physically related to these other ones. Yeah.
So I guess a follow-up question from Igor is, do you have any examples of model improvements? Not just the results, but has this led to any model improvements?
Yeah, we haven't done that work yet. That is where we want to head. So I did this work with a small team without any modelers on the team, and we would love to, in the future, to collaborate with modelers and see where we can get with this.
Maria, do you have any examples?
Yeah, that's really where we want to go, right? And so that's what we're looking at ahead with predicting model errors, right? So if we can identify where the sources of predictability are coming from for predicting errors in our modeling system. And so we really are focusing on climate timescales or subseasonal to seasonal, et cetera, timescales. So if we can identify the source of predictability for some of these errors, then we have to evaluate whether that's model related or just inherent limit of predictability of the Earth system. But absolutely great point, and something that we have our eyes on.
Thank you. And Zach, do you want to ask a question to Jake?
Yeah, sure. So I was a bit curious about your causal network approach. So this method I've looked a little bit myself, and one challenge I've had when using this is you're using linear lagged correlations to find those connections. And with something like sea ice, it varies more slowly usually in the time series than something like wind or humidity. So in that instance, sea ice's biggest predictor would be past values of itself instead of something like wind or humidity. So I'm not curious if you've encountered any challenges with that and if you've been able to resolve it.
Yeah, so we're working on the validation part of that work. So when you talk about linear and lagged correlations, what that reminds me of is Granger causality primarily does that, and it's a usually bivariate method, and that does have those problems. That's been around for a while. We now say X Granger causes Y when we use that method rather than cause. There are some newer methods that look to solve a lot of those problems. So the one that I've been applying is called PCMCI, and that explaining that long acronym wouldn't help. But if you Google PCMCI, you'd find it, or Tigermite is the name of the library. these are, these use iterative conditional independence tests that can be linear or nonlinear and non-parametric as well. And they look at, and there's even a one that's adapted for contemporaneous effects. So when things are happening, causing things instantaneously, it can be tolerant to that, but that is a problem. So if you're looking for a cause that is happening on a smaller scale than what's being measured, you're just going to miss it. So that's a big issue with what you're studying. Trying to think of, so another popular method these days is well, it's growing in popularity right now, but it's been around for a little while, called structural causal modeling, that is meant not to have those problems as well. Yeah.
Great, thank you.
All right, I hand it over to Vladimir. Do you want to continue the discussion?
Oh, yeah, I actually inserted a comment about the amount of data. So we get tons of data from satellites, but they are not necessarily very independent. We may not need data every day to predict, let's say, sea ice minimum in September. So that's one thing. So we actually don't have too much data to develop, observe data to develop reliable algorithms based on observations. One other important thing is that some data contradict other data. So how would you integrate those factors in your machine learning? One of the biggest problems, I think, is, for example, measuring sea ice thickness, and people do all kind of tricks to make sense out of observations. Snow on ice is a big variable that people do not understand. So there's a lot of questions about the physics, and we are dumping all of it in our black box and hoping that black box will digest this whole thing and come up with a magic solution. So I think the lack of physics is one of the problems, and I'm sure you're aware of that, of ML in general. Lack of physics in this black box. So I'm not sure what the question is. So what's your take on it?
I have a few thoughts that came to mind. Not a sea ice expert, but yeah, I think it's really interesting. Several points that you raised. So regarding your sample size or the amount of data being limited, earlier I mentioned transfer learning, where you can leverage different types of products to retrain and continue training and learning. So for example, with multi-year prediction of El Nino, there's a big paper that was published a few years ago, Ham et al. In Nature, where they were able to skillfully predict El Nino with with over a year lead time, overcoming the springtime predictability barrier by leveraging both model output and observational data. So first training on one data product and then continuing to train, so your weights in your neural network would get updated and shift towards predicting the observational product. But there are also other methods that are being developed for limited data problems, because this is a common issue. So for example, there are Siamese models. I have not used them, but they have been suggested to me to use for any problem that may have a limited availability of data, to try to, again, overcome some of these issues. Because of course, in the Earth system, for some certain observational systems have only been deployed in recent years. And regarding the physics of the model, or at least physical constraints. So for example, precipitation, we know there can't be negative precipitation. So a neural network should not be predicting negative precipitation, right? So there are some very simple physical constraints that can be incorporated in the architecture of the neural network. And so that can be done in a few different ways. So for example, using some sort of custom loss function that the network would use to learn. And so incorporating that constraint, or even the physics of your system in there. Now, regarding the fact that that we maybe don't understand certain aspects of sea ice, I'm not sure, but like Jake mentioned earlier, just really becoming familiar with the data and the pre-processing of the data before even feeding it into a neural network is really important. We shouldn't just be taking our data and dumping it into a neural network and hoping for the best. We really do have to make sure that we frame the problem in the way that will give us the answer that we want, right? Making sure that the network is answering the question that we need answering, and making sure we're pre-processing our data in the way that will give us that as well and help the neural network converge on a solution. So for example, with subseasonal prediction, removing certain oscillations or signals is absolutely critical before even beginning to train. And that requires very much a physical understanding of whatever system you're using. And Jake, any thoughts as well?
Well, I wholeheartedly agree. In most of my work so far, we've done this very naively by just taking average values from the Arctic and throwing them into the model and looking for results. And I've recently been learning about ways that we can do that a lot smarter that the climate community has been using for a little while with EOFs and which are basically principal component analyses to get more representative quantities of the values that we're interested in. And in the causal work we're doing, the what your scientific question is very, very important. And I think that applies to all of this kind of work. If you were to run a randomized trial on this, which we know we can't do in the climate, but if you were, what would you be looking for? What is the design you would create, and how would you use it to answer your questions? I think thinking through in that way can help define the data and the analysis that you want to come up with eventually.
All right, great guys. It was a wonderful discussion. We're running out of time, unfortunately. If anybody has any questions for Maria or for Jake, then please send it to them directly. And with this, I'll hand it over back to Hazel.
Thanks, Wilbert, and thank you, Maria and Jake, for really wonderful presentations, and everyone for a good, engaging discussion. I just wanted to share, I think it'd be relevant for everyone on this call, that IARPC is releasing a new 5-year Arctic research plan, and that'll be coming out December 15th if you're going to AGU, and then December 16th, there'll be a launch event if you're not. So I will put some links for that in the chat. Both technology and modeling are highlighted in the foundational activities section of that next plan. So you can anticipate a lot of exciting activity sort of similar to this call in the next 5 years. So I just wanted to share that with you all, and thanks again, and I hope you have a wonderful day and a wonderful week.
All right, thank you everybody, and especially Maria and Jake. Thanks, appreciate it.
Yeah, thanks for inviting us. Yeah.
Take care.